So the talk is on fixed points of non-negative neural networks. So I think it is best to explain first why fixed points and why non-negative networks are of our interest, so that we have some motivation to go on with the subject. So why non-negative networks first? Why non-negativity? Right. So if you look first at the input-output relationship, then for just a standard neural network architecture you can think of, such as an autoencoder, for example, then it is quite common to have a non-negative inputs, right? Because the images, the text processing, how the input data is formatted, it is usually as a non-negative set of non-negative vector set of numbers. And beyond that, at the spectral analysis, and you have the power spectra, the power is also non-negative by the laws of physics. So that's simple. The more difficult justification is about why we have to consider non-negative weights. And this has been explored that's not our idea, it has been explored in literature for the last maybe 15, 20 years. Maybe the most common justification, the reason that we consider non-negative weights is that the resulting networks have some explainability, like inherent explainability, in the sense that the weights can be interpreted. That's because the weights can only be added, right? That there's no subtraction. And that's how our brains process sensory information, right? So when we look at our world, what we see is the set of particular elements of the image, and they are in our brain that combine into the whole thing that we see. So that's a very nice biological motivation. And also, there's a recent motivation that has come out mostly from IBM, but I think many other smaller, less, the smaller companies, some startups also work on this beyond IBM, is that there's a recent resurgence of analog neural networks, but not in such a valve, old-time style analog neural networks, but rather very efficient, energy efficient, and very very small in implementation, right? So for analog neural networks, we have the weights are the resistors. So the resistance is also non-negative by physics, right? So there's also a very nice practical motivation. Okay, so that's non-negativity. How about the fixed points, right? So the motivation is that if you look at the autoencoders, then the fixed points are exactly the inputs that can be perfectly reconstructed, right? If you have the same output for a given input, then it means that the output reproduces the input. That's the fixed point of the autoencoder. But also, if you look at the iterative methods for learning, or methods such as loop unrolling, if you want to solve some inverse problems in this way, then the cost function, which is being optimized iteratively, for example, gradient descent type, right? As the simple example given here, they can be also recast as a fixed point, finding a fixed point problem of a given a mapping which depends on the cost function, right? Such as the example here. And also, the final motivation due to Mateusz Gabor is that these are, it turned out to be that the deep equilibrium networks, the equilibrium here basically means fixed point networks. They are also quite recently quite popular, and our motivation also comes from exploring such networks. Okay, so non-negativity and fixed points justified. So let's move on to some simple mathematical facts that we found first. First, the model, that's just a standard feed-forward model. There's nothing fancy in it. Even the notation is standard. right? So sigma i's are the activation functions and so on. We have n layers. And I would like to just to mention one thing which is quite maybe less obvious application of the fixed point theory in this paradigm is that if we have the electro or magnet or let's say electroencephalography, EEG, right, for the brain, for those interested in brain signal processing. That's just a small digression. But if you're interested in brain signal processing, then there's the EEG. You record the potentials at the electrodes of the working brain. That's the forward problem, connects the sources of the activity with the potentials you record at the electrodes, and then you want to solve the inverse problem based on the measured measurements. You want to actually reconstruct the activity of the sources. So if you want to solve both the forward and inverse problem simultaneously, basically you can construct an autoencoder, and you want to look for the fixed points of such an autoencoder. Of course, the devil's in the detail, but the basic idea is quite simple. Okay, so we have a standard neural network model, and the first result that we got. Now we are coming to the math part. There will be like 4 slides with some maths in it, but that's just about it. Okay, so the first result we found is that with our assumptions, right? So non-negative weights, non-negative inputs and outputs, the network with such constraints is monotonic. That's monotonicity, a very simple concept, and scalable. Right? In a sense, it doesn't grow too fast, right? So that we have some scalar rho, and it limits the speed when the function grows, right? These are not our assumptions, right? These are the consequences of the non-negativity, right? So it's just not that we have to assume that the network satisfies those properties. This is actually derived from the non-negativity assumptions. And actually, there's even stronger version of it, is that if we have a sigmoid activation function on at least one layer, or the weights are not only non-negative, but actually positive on at least a single layer, then then the resulting network is strongly scalable. Okay. So actually, in mathematics, the monotonicity is called order-preserving network and mapping, and this is also called not scalable but subhomogeneous mapping. Okay. But these are the mathematical terms. I mean, the concepts are simple. Don't grow too fast, and it's monotonic. Okay. So, thanks to those two properties, monotonicity and scalability, we are able to use the nonlinear Perron-Frobenius theory. Perron-Frobenius is quite a well-established theory for settings where things are positive, and those two properties are crucial, right? The monotonicity and scalability. Namely, if the network is such, and we have it proved, then we can associate with such a neural network an asymptotic mapping for this network. This is as mathematics as going to get. There's nothing beyond that. Okay, so just one thing that we have to take notice. Okay, so we can associate with a given non-negative network, we can associate an asymptotic mapping with it. Okay, that's the expression. The limit is well defined for such networks, and this asymptotic mapping is always homogeneous, positive homogeneous. So we can find the spectral radius for such a positive homogeneous mapping. And actually we found that for the neural network, the asymptotic mapping is not only homogeneous, positive homogeneous is actually linear, okay, and very simple at that, very simple linear mapping. Basically, we have the result that the asymptotic mapping is either just a zero mapping, so everything is mapped to zero, in cases where on at least one layer we have like slowly increasing activation functions such as tanh or sigmoid, or it is a product of all the weight matrices, all weight matrices across the layers, if otherwise, right? So if all activation functions are not just slowly growing, such as ReLU, let's say. It's just identity on the R+, or swish or mish or such kind. Okay. And so basically we can compute since we have the very nice, very simple form of the asymptotic mapping, we can compute the spectral radius, right? So it's either the maximal eigenvalue or just 0. Okay. So that's our first result, is that if we have a neural network that is monotonic and weakly scalable, basically non-negativity implies those conditions, and it is not too sparse. Not too sparse is implied by this condition that it doesn't grow, and that it does grow fast enough, yeah, at the fixed point. So so basically the sufficient condition for this fast enough growth is the network being not too sparse. Okay, and the spectral radius is less than 1, then the fixed point set is an interval. So very simple fixed point set, which is good for some applications such as deep equilibrium networks, but is bad for such applications such as, yes, autoencoders, right? Because there's only basically one rescaled input that you can perfectly recover. But that can be perfectly recovered. But perfection, and I will come to this point later, is usually not something we aim for in practice, right? Sufficiently good is what we are after, not perfection, right? Okay. So basically, if you look at the previous slide, so for example, if you use the sigmoidon on this one layer, then the asymptotic mapping is just 0. So this condition trivially holds. And what separates this result from the results of combats and people using the experts in convex analysis who now apply the convex analysis to neural networks, machine learning in general, is that there's no condition on the weights of the matrix. There's no condition on the norm of the weight operators, weight matrices, right? Because, yes. Sorry? Yeah, that's the spectral radius. So if we have the asymptotic mapping, which is just 0, then the spectral radius is also 0, and this condition is just trivially satisfied. Okay. So there is no constraint on the weights on matrices. The norms on weight matrices, norms of weight matrices. So there's no need for normalization. For the convex analysis approach, since they use the Lipschitz constant always involves the norm of the weight matrices, right? There's nothing like that here. So that's really good. The cause is that we have a non-negative network, right? There's no magic here. We have another additional assumption they don't have, but we have a benefit they have to, that we don't have to care for the norms of the weights. All right. So just one more result, which is actually a special case from the result derived in 2019, is that for the special case, the network is not only weakly scalable, but actually scalable. So the stronger condition, then basically the interval fixed point set degenerates to a point, right? So basically the interval just collapses to the point. All right. So now, since we basically solved the problem of the shape of the fixed point set for the non-negative, weakly scalable and monotonic networks, now our main aim is to relax those conditions, right? Because we need to aim for some richer fixed point set and the approximate fixed point set. So, for example, there's also very strong trend these days in machine learning on monotonic networks, not weakly scalable, just monotonic networks, right? So the monotonicity can be obtained. The sufficient condition for monotonicity is that if you have the weight operators are non-negative, but you can admit the negative biases as long as on this given layer with negative biases, you use globally non-negative monotonic. So, for example, a ReLU activation function, right? And also, if you have an activation function which is only monotonic, not weakly scalable, just monotonic, like switch, mish, GALU, right? then the biases, you have to keep non-negative biases on this particular network. And for this relaxed version of a just non-negative monotonic network, we have the result that basically you can always achieve the least fixed point starting from the iteration, the fixed point iteration from the zero vector, right? So you are guaranteed to obtain the least fixed point of such a network. Very useful result in practice. Okay. So just to summarize with some simple, I mean, that's the Minis data set. For the proper application, look for, I strongly advertise the Mateusz's result for the deep equilibrium networks. That's like a real result. Here we just have more like a toy example. But basically we wanted to emphasize that we don't have to care for the norms of the weights. Okay, so they can be smaller than one, they can be larger than one, the product. The norms can be the norms of the weights can be arbitrary. We don't have to care for this. That simplifies implementation. All right, so now we have just a couple of open questions. First, we have to find out, yes, what are the approximate fixed point sets, right? Because that's, as I mentioned, that's something we want to, if you want to make it practical, then the question, how sufficiently good is sufficient? For example, for the reconstruction, that's one point. The training efficiencies is another we have to consider. And maybe the point number 4 is of, now I think it's something we are working on, is that we want to expand the expressibility of non-negative neural networks. We have met with Professor Podzio, yes, like 1 year ago, and he told us that basically that there's a possibility that just a slight relaxation of the assumptions that we have can lead to much greater expressibility of such networks. So like an approximation theorem for such relaxed non-negative neural networks will be very useful, right, to convince people that such networks make sense. So that is all. Thank you very much.